Hello, everyone, and welcome to today's webinar presented by Líbilo software. Today, we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is blast time history analysis in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be answering all of your questions that you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. Now, we always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So I wanted to go over the various content that we'll be covering over the next hour today. The first will be just the general blast loading design concept. And for this, we'll be primarily referring to AISC Design Guide 26, as well as some references to the UFC 3-340-02 documents. Then we'll move into our first example. And this example today is going to be taken again from Design Guide 26, and we'll go ahead and model this within RFEM. Now, we're also going to be utilizing a few different add-on modules within the program as well. And the first is RF-DYNAM Pro Natural Vibrations. So this will allow us to run a natural vibration analysis for our structure to determine the angular frequencies, the natural frequencies, and natural periods. Then we'll move on to a linear time history analysis utilizing RF-DYNAM Pro forced vibrations. And finally, we'll take into account any material or geometric nonlinearities with the additional add-on module extension, RF-DYNAM Pro nonlinear time history. And through all out of this, we'll definitely be looking at the structure response as well as the results evaluation for each one of these results. Okay, so getting into the blast loading basics. As I mentioned, we're primarily going to be referring to the AISC Design Guide 26, Design of Blast Resistant Structures. We'll also be making some reference to the United Facilities Criteria 3-340-02 structures to resist the effects of accidental explosions. Now, there are many more references out there for blast time history, but for today's example, I wanted to specifically refer to Design Guide 26 because this simplifies the time history analysis quite a bit and was just the best guide for today's example within the program. Now, what are the factors influencing structural damage when we talk about these types of explosions? Well, we know that the structure material is definitely going to play a role, as well as the overall mass and stiffness. What else is important to know is the explosion type, as well as the distance to the structure. Now, clearly, a larger explosion that is closer proximity to our target structure is going to cause a lot more structural damage than what we'd see from a smaller explosion located further away. And finally, the blast orientation to the structure. Is this located at ground level? Is it up in the air? What proximity to the structure? And of course, if we are located in an urban environment, do we have surrounding structures that we need to consider as well? Now, the ultimate goal here is not necessarily to avoid extensive structural damage. This is inevitable when we're talking about these extremely high loads applied to our structure, but rather what we're hoping to do is to avoid loss of life. So we don't want to see complete failure with the particular infrastructure. Now, steel is often used as a primary structural system for blast loads just due to the large inelastic deformation capability. So we're talking about the plastic phase here without the loss of load carrying ability. But in turn, we know that concrete may have a higher mass and stiffness than what we would see with steel structures, as well as a higher resistance to high temperatures. So steel, we might see much more melting of the material, and concrete can withstand those temperatures a little bit better. Now, as far as the blast load application in terms of a time history, over on the right-hand side, we have what's called an idealized pressure time history for blast loads. And there are certainly several theoretical approaches for exactly plotting this particular curve over on the right that we're seeing. Just to cover a few of the basics, let's first begin with the peak overpressure. So this is the pressure above the ambient atmospheric pressure, hence the name overpressure. And this will be an instantaneous pressure that arrives at the structure. So we can see within this diagram over here, we have a short period where nothing happens until the time of arrival, and then that instantaneous rise for the peak overpressure applied to the structure. The positive phase duration is the time period that it takes for the pressure to return back to ambient or back to zero. And we can see that indicated over here in the positive portion of the diagram. We also have what's called the positive impulse, and this is the total pressure time energy applied during the positive duration. So this is the area under the curve. And finally, we have the negative phase duration. Well, this includes the energy, again, the impulse, which is going to be the area underneath the curve that follows this positive phase where the pressure falls below the atmospheric pressure. So turning to the two different lines that you're noticing on this particular diagram that we see here, we have the reflected blast load shown in a solid line, and then the free field blast load shown with a dotted line. So what exactly are the differences here? We'll start off first with the free field blast load indicated by this dotted line. You notice the magnitude is much lower here. And this is what we call the free field or side-on blast load, where the blast wave actually travels parallel to a surface. More or less, it's just sweeping over this surface with no impeding objects. We might see this with sidewalls, with roof elements, with our rear wall, which is definitely what we'll be noticing with today's example. Typically, in most literature, we'll see the subscript SO used for side-on. Now, we also have the reflected blast load, and this is where the blast wave will strike at an angled surface other than parallel. So a perfect example of this would be any surface that is normal to the explosion, so some type of front-facing facade, for example. And obviously, we're going to have much higher pressures here than what we'd see with a wave sweeping over some of those other surfaces that are parallel to it. So we calculate this reflected pressure with what's called the reflected pressure coefficient multiplied by the side-on pressure given by this equation here. And referring now to the UFC document, there is a nice figure here, 2-193. And you'll notice that the angle of incidence is given here on our x-axis. Then we would locate our peak incident overpressure. We can follow this along to determine what our reflected pressure coefficient should be. So what exactly is the angle of incidence? Well, if we look at this small diagram over here on the lower left, we have our initial blast wave direction. It is going to reflect off of this surface normal, so 90-degree angle here, which will produce an angle of incidence. And this is the value here that we want to locate within this figure to determine what that coefficient will be in order to increase those reflected pressure loads. So moving on to the blast load simplification. So again, we're primarily referring here to AISC Design Guide 26. And let's first start off with the pressure time history positive phase. Well, what we're going to do here is to simplify it to a triangular distribution, but we still want to maintain that instantaneous rise as well as a linear decay now. So quite a simple application when we compare it to the more theoretical approach shown in the background here. Now, it's important, though, that the peak pressure as well as the impulse are preserved. And remember, the impulse is the area underneath the curve. So therefore, we have to come up with some other fictitious duration here. in order to maintain both P and I. And this is estimated to be approximately 2 times I over P. So when we're talking about the negative phase, we're actually going to neglect this for the demonstration today just for simplicity. Now, as engineers, we don't necessarily always want to neglect this. It could be important when we have elements on our structure that are weaker in the reverse loading direction, or we should also consider it for short natural periods compared to the load duration. Now, some other considerations that we will not be taking into account today include the drag forces due to wind or dynamic pressures. Do we have a large wind load following up along with this blast wave as well? And both the Design Guide 26, the UFC document, many other, I'm sure, all give consideration to these drag forces. Do we have large openings to account for the interior loads due to leakage? So essentially, small openings aren't going to have that much of an impact, but when we have large openings on the structure, the load actually leaks to the interior, and we now have these interior loads that we would also need to account for. And finally, is our target structure in a very urban environment? And on the positive side, we have what we can consider shielding, which is load reduction. When we have a blast wave and we have many other objects in front of our target structure, then of course the load will be reduced. But on the downside, we have what's called reflection, where the load can actually be amplified because it's reflecting off of all of these different objects directly onto our target structure. So let's take a turn now from these basics and we'll take a look at RFEM, which is our finite element analysis software. This is the main program where we'll fully model the structure. We can load it with general static loads and run a full analysis. But when we're talking about dynamics or any type of time history, we do need to utilize our dynamic add-on modules. And we actually have a total of 4 of them. The first is RF-DYNAM Pro natural vibration. So this is a prerequisite. We have to go ahead and run the natural vibration analysis before we consider any of the rest of these dynamic analyses listed here. This is going to run the eigenvalue analysis, determine the mode shapes. We can take a look at angular frequencies, natural periods, and we'll definitely be doing that today. The second add-on module, RF-DYNAM Pro equivalent loads. So we actually will not be getting into this add-on module today. It is much more focused on seismic and in particular a response spectrum analysis according to the AISC 7, the NBC, and various international codes as well. Now, I've done previous webinars on this topic, so certainly refer to our website and YouTube channel if you want to learn more about that, but we won't be getting into that today again. RF-DYNAM Pro force vibrations does allow us to run a limited response spectra analysis. We can also take into consideration accelerograms, but what we'll be utilizing it for today is to run a linear time history analysis for these blast loads. And finally, we have RF-DYNAM Pro nonlinear time history, and this is actually a module extension. So you have to have RF-DYNAM Pro force vibrations in order to activate this add-on module extension, and it's really just going to release these nonlinear solvers for both accelegrams, but for our case today for nonlinear time history to take into consideration material and geometric nonlinearities. So again, a summary here of what we'll be utilizing includes these 3 add-on modules listed. So now moving on to our example. Again, I'll be referring to AISC Design Guide 26 and in particular example 2.1. And so the example within RFEM will fall very closely with this today. We can see over on the right-hand side, again, directly from Design Guide 26, a plan view of our structure as well as an elevation view. It is a 1-story steel building and the dimensions include a 50-foot width, a 70-foot length, and then we have 15 feet in height. In the short direction, we will have braced frames, and in the long direction, we have rigid frames. Everything will be composed of hot rolled steel sections, and then for my roof deck as well as my wall panels, we will be modeling ribbed metal surfaces here. Now, the blast load will take place, and we can see that indicated over here on the left, with a charge weight of 500 pounds, and it is 50 feet away from the structure. So we can see it's normal to this front short face here. So in order to consider the time diagrams for our time history analysis, we actually need to now move through the solution to determine what all of these different variables are. So we begin with the scale distance, and this is indicated by the variable z. Z is given to us by r over the cubed root of w, which is just simply 50 feet away from the structure with a charge weight of 500 pounds. Then we're going to get 6.3. So on the right-hand side, you'll notice an additional figure taken from that UFC document, figure 2-15. And this plot is showing the air blast parameters versus the scale distance. So we see the scale distance z that we just solved for on the bottom x-axis. And now there are some assumptions here with using this particular figure. You can see it's a positive phase shockwave parameters for a hemispherical explosion. So not spherical, not located up in the air, but located at ground level and also at sea level. So if you have a target structure that you're designing a blast load for something other than sea level, there are scaling approaches that you can take to kind of scale this to meet those needs. Now, it's also conservative here to assume a fully reflected surface, and that's what this plot is giving to us here. So how exactly do we use this chart? Well, we just solved for z equal to 6.3. So we just simply find that along the lower x-axis here, follow that up, and all of these various lines are going to provide to us our different parameters for that idealized pressure time history curve. So they're summarized within this table. So from figure 2-15, we can see here the reflected peak pressure, the side-on peak pressure, reflected impulse, side-on impulse, and so on. Now, some of these are still dependent on the charge weight, so it requires one step further to calculate that. It's quite easy. And then we get all of our calculated values here. So this figure can be extremely helpful when we want to go ahead and solve for these air blast parameters. All right, so let's talk about the reflected pressure. This would be applied to the front wall. And we are going to take Design Guide 26 approach with the equivalent triangular shape here. And we want to utilize the peak pressure, P sub r, and the impulse, I sub r, and we want to preserve these values. So we can see these given to us over on the right-hand side here, but remember on the previous slide, we got this information, P sub r and I sub r, directly from this figure. So it's easy enough to come up with this equivalent duration for the positive phase blast load with the estimated value of 2I over R, which is equal to 6.19 milliseconds. And sure enough, this is all that is required for our reflected pressure for the front wall time diagram. So moving on to the sidewalls and the roof, what we'll be applying here is the side-on pressure. So this is going to be, remember, that smaller triangle here within our idealized curve. And for simplicity as well as the conservative approach, we're actually going to use the same scale distance Z that we use for the front wall center line, also for the sidewalls and roof. Now, realistically, we could maybe calculate a larger Z to decrease our magnitudes, but again, for simplicity and the conservative approach, we'll just use those same values. Therefore, we need to calculate here T sub E. We have P sub O and I sub O from the previous slide. So 2I over P is going to be equal to 7.71 milliseconds. And this is all that is needed for our time diagram for the sidewalls and the roof. Now, the final step here is the rear wall, which is a little bit different than what we just saw with the previous two structure portions. The advantage here is that our charge distance is going to be increased. So we have our blast taking place at about 50 feet away from the structure face. Well, we can also consider the full length of the structure here of 70 feet. So our new charge distance is now 120 feet. So we calculate that with the scale distance here with that new R value, and we get 15.1. So you can see at the front of the structure, we have Z equal to 6.3. At the rear, we have Z equal to 15.1. So once again, we refer back to the UFC document to figure 2-15. We take a look at Z equal to 15.1, and here is a summary of all of our parameters. Now, you'll notice that I only listed here the side-on peak pressure and the side-on impulse rather than reflected. This blast load is going to sweep over the rear wall. We don't have any type of reflected load occurring here, so that higher magnitude is not of interest to us. Now, we do need to calculate that equivalent duration for the positive phase blast load. And again, we go ahead and run this calculation with 2I over P using this data here with our new Z value, and we get 19.1 milliseconds. Now, it's also slightly different here in that for our rear wall, it's going to take the wave, the blast wave, a little bit of time in order to ramp up to that full peak pressure. It's not instantaneous like what we're seeing with the front, side, and roof. So how do we calculate this? Well, we know the estimated time of arrival is 66 milliseconds. We calculated that from figure 2-15. What we now need to calculate is this time to the peak pressure, T2. And that's really easy to calculate because how we'll do this is to take into consideration T sub A here, which is the time of arrival, and we're going to add on L1 over U, where L1 is the span of the element parallel to the traveling wave. And in our case today, it's how long is it going to take for this charge to reach the top of the wall, and that's 15 feet in height. U is going to be the shock front velocity given to us back a couple slides ago from the UFC figure 2-15. So we have this length, we divide it by velocity, we get a time, and ultimately we get 77.9 for T sub 2 here. Now the time to the end of the blast, this is just going to be T sub 2. And we're going to add on that estimated time that we calculated on the last slide of 19.1 milliseconds, and we get 97 milliseconds. So let us take a look at the summary here for all three portions of our structure so we can kind of see how this blast load is moving from the front of the structure to the rear of the structure. So over on the right-hand side, you'll see a plot here showing the pressure versus the time of the blast wave. And the green indicates the front wall. The orange is going to indicate both the side walls and the roof. And finally, you can see a little bit later on, we have the charge reaching the rear wall. So over on the y-axis is going to be the pressure. We would fully expect the highest pressure to be applied to that front wall, significantly less to the side walls and roof, because remember that charge or that blast load is just sweeping over those surfaces. And finally, the rear wall will be relatively low as well. A few assumptions that I just wanted to reiterate. Of course, we're using this equivalent triangular loading function over the more exact loading function. Plenty of more theoretical equations, such as the Friedlander approach, if you wanted to calculate that curve exactly. We are going to neglect the negative phase of the shock, as well as some of these other variables I mentioned, dynamic pressure, openings, and so on. And finally, for simplicity, the full side-on pressures computed for the non-reflected surfaces. So this includes the sidewalls, the roof, the rear wall. This is the full value here. Rather, in the UFC document, there are load averaging techniques to decrease this magnitude. So a lot of the approaches that we took today are definitely the more simplistic, but also the more conservative approach. UFC will have much more information if you want to get into more detailed analysis. All right, so now we are ready to get into RFEM. So you'll see the structure already modeled here. This is exactly from the PowerPoint as well as Design Guide 26 that I mentioned. It is just a basic one-story steel structure. and it is 50 feet in width. We have 70 feet in length and 15 feet in height. And we're going to assume that the explosion happens over here on the left-hand side, normal to this front face that we're seeing here. To quickly just cover a few of the cross sections that I've used in this example. So for my columns, you'll see I have W14 by 193. When we look up at the roof, we'll see here W18 by 130. Those used for those main beams and main girders. We also have our purlins, which are going to be channel sections. So channel 10 by 25. And then we also have our girts, which are, again, channels C10 by 30 sections. It's also important to know, and if I highlight these elements here, we have a couple of X braces. So remember, in the problem statement, we have brace frames in the short direction and we have moment frames in the long direction. Well, I added this lateral bracing here, and if I double click on it, you'll see that these are tension only members. So in the program, these will take only tension forces. It's some type of cable element, we'll assume. So when the program experiences compression within these elements, it will completely take it out of the analysis, but RFEM being a nonlinear analysis, it can reactivate these if we see tension again in a subsequent iteration. So let's just keep that in mind for those X braces. Now, looking at the surfaces, so for both the roof and the walls, what I went ahead and modeled here are orthotropic stiffness surfaces. And it's just a general steel A653 grade 40 material. When we go into the detail settings of this orthotropic stiffness, we'll see that I have set this to a trapezoidal sheet. And what's convenient with this option is under the second tab, I can just simply put in the sheet thickness. I can put in some of the geometric variables for my ribs, including spacing and so on. And the program will automatically calculate my stiffness matrix for me. So this is definitely going to add a lot of lateral stability to our structure at that roof level. And I went ahead and used it for the wall elements as well. All right, so that is a basic overview here of our surface elements as well as our members. So under my display, what I'll do is to go ahead and turn off my dimensions here. And let us discuss the loading. So I've created 4 separate load cases here. The first is going to be self-weight, and the self-weight is exactly as it sounds. It will account for the self-weight internally of all of our members and surfaces automatically, but I've also added in here just a general line load, or sorry, member load up at the roof level to those main beams and girders, 0.1 kips per foot, to account for any additional dead load that we may have up there. Now, the next load is going to be for my front wall. And we can see this load applied as an area load. This is to initially account for that blast load acting on this front surface. So this area load here is a bit special because it's going to convert the area load to member load. So I'm not necessarily applying it to this surface, but rather I want it to be applied directly to these main lateral resisting frames. And you can see that the magnitude is set at 1 psi. We want to use a very arbitrary value of 1.0 here. Later on in the time diagram, I'm going to tell the program how this magnitude will increase or decrease and vary over time with the actual time history analysis. But for now, we want to set this to 1.0. So you can see that with this front area load, if I right click and I display separately, we can see those as member loads based on their tributary width applied directly to those frame elements. In a similar fashion, if we take a look at load case 3 here, we have area loads on the sidewalls as well as area loads on the roof. And once again, all of the magnitudes are 1 psi. If I right click and I display separately, you'll notice that I applied them to those main frame elements. I did not apply them to any of the channel sections for the girts or the purlins. And again, I did not apply directly to the surface. I'm more interested in the structural response of these main elements included in our frames. And finally, we'll take a look at our last load case here, and we have a area load applied to the rear of the structure. So normal to that rear facing wall, 1 PSI. I can right click to display separately, and we see those member area loads applied directly to those elements as well. So a very basic application here. Now, we're not going to spend any more time within RFEM, but rather we want to move into the dynamic analysis. So what I'm going to do is to launch RF-DYNAM Pro, and we can see in our project navigator, here is our long list of add-on modules. So you can find RF-DYNAM Pro here, or we can go up to the add-on modules and we can find it maybe categorized a little bit better under dynamic, and we launch RF-DYNAM Pro. So this add-on module is going to be nothing more than just a simple dialog box that pops up. And here are those 4 different dynamic modules that we discussed in the PowerPoint. And you'll notice by default, the first one activated is RF-DYNAM Pro natural vibration. So again, this is a prerequisite. We have to run this natural vibration analysis before we move on to any of the additional add-on modules. I also can activate here my mask combinations tab, and we'll get an additional option here. This is if we wanted to combine multiple mask cases into a combination. I won't be doing that for today's example, but that is an option. So really, we just need to move from left to right here with our tabs. So the first mask case, I'm actually going to import in, if you remember, that first load case, which includes self-weight as well as that member load applied to the roof structure for those various elements. Now I'm going to uncheck here from self-weight of structure. If I leave this checked, we're accounting for self-weight twice, which would be incorrect. Now we also have the ability to define additional masses at nodes, lines, member services. We can deactivate masses, so a lot of possibilities here. But for now, we'll just stick with this single mass case and move on to our natural vibration cases. So we want to initially tell the program how many eigenvalues to calculate. For my structure today, I'll set this to 30. The scaling of the mode shapes, will leave this as the square root sum of the squares, and we can move on to the calculation parameters. So under this dropdown, we want to select either our mass case or our mass combination of our acting masses that we want to consider for the natural vibration analysis. Now in our case today, we only have 1 mass case, so that's what's available. As far as the directions or about which axes this mass is acting, this is somewhat dependent on the type of mass matrix. So you'll notice with the diagonal matrix, translational degrees of freedom, some of these options above are grayed out, but as we scroll through these, translational and torsional degrees of freedom, rotational, we have different options available to us. So we'll be moving forward with the diagonal matrix translational degrees of freedom for today, as well as the general Langkos solver. Now, our help file, which you can locate down here at the lower left-hand corner, will give much more theoretical background on some of these different options and how maybe it can improve the calculation for your particular structure. So once we are done setting all of our natural vibration case data, we can go ahead and run the calculation, and you'll actually see for today's example, this solves rather quickly. So we are presented with our results of the dynamic analysis back in RFEM. Now we're technically still within this add-on module. We can see this from the drop-down box here. We also want to view this information in table 5 for dynamic analysis. And what you'll notice within this table, and sorry about that, let me go ahead and redock my tables here, is the natural vibration case is given to us within this dropdown. That's all that we've solved for. But right next to us are all of the 30 mode shapes that we told the program to solve for. So we can scroll through these different mode shapes just to kind of see how the structure is responding under the given frequencies. Now, I always recommend to immediately jump to this effective modal mass factors tab. And what this tells me, if I scroll all the way to the bottom, is the mass participation. And this is shown at 95% in the X direction for a sum of all 30 of our eigenvalues, and 96% for a sum of all of the eigenvalues in the Y direction. So this is great mass participation. We like to see something around 90% or more. What else I want to pay careful attention to is what we call the dominant modes. So if I look at a lot of these early modes, really don't have much mass participation going on until we get down to mode shape 13. And we have 74% participation in the X direction. Then I go a little bit further and I see my dominant mode in the Y direction. So this is 68% in the Y direction. And what might also be helpful too is under our views tab, we can deactivate our surfaces here. Maybe we increase our deformation. So we can see we're really getting a response of the structure as a whole. Now, of course, there's some maybe what we call more local modes with these girts, but overall, this is certainly our dominant mode in the Y direction. So keeping in mind mode shape 13 and 18, we jump back to this first table here, natural frequencies. And I'm going to highlight, let's take a look at mode shape 13 as well as mode shape 18. So for these two dominant modes, I can now determine what my angular frequency is, my natural frequency, and my natural period. Now, we might be thinking, well, what does this really matter for a time history analysis? But this actually does come into play a little bit later on when we're talking about damping considerations. So we'll just leave this highlighted in the background for now. It's great to understand which is our dominant modes for the structure for the natural vibration analysis. So let us go back into RF-DYNAM Pro then. And what we can do now is to activate RF-DYNAM Pro force vibrations for time diagrams. And we get two additional tabs up at the top. So everything that we've just input for the natural vibration case, that remains the same. So no changes to be made there. But now we want to move on to our time diagrams tab. So this is where we are going to input the information that we solve for within the PowerPoint to tell the program how these loads that I've applied back in RFEM as load cases will vary with magnitude and over time due to this blast load. So the first time diagram that we want to specify is going to be our front wall. And I am going to jump back here to the PowerPoint just to give a little refresher. We might be interested in seeing again what the time diagram would look like for this front wall. And remember, using the simplified approach, we have a short time period until the time period of arrival. We have an instantaneous pressure clear up to 79.5 psi and then a linear decay back to 0. So all of our points are given here in terms of pressure and time, and this is the information that we want to input in to the program. So for the first time step, we will specify a transient option. And transient just means that we can input each individual time steps here. So that's what we'll be utilizing today. Now, in turn, we can utilize a periodic option. And this would be interesting for us for rotating machinery, for example, where we put in an angular frequency as well as a phase shift. And finally, there is the ability to input in a function. So we can actually define variables and parameters. This would be extremely useful if we were taking the more theoretical approach for the idealized pressure time history curve. So for example, the Friedlander equation, we could actually input in. So we do have some additional resources here that I can relay to you if you are interested in seeing that more theoretical approach with this function option. So just reach out to us if you are interested in that. But for today, taking this transient approach with the more simplified application, we want to go ahead and input in these time steps. So the first time step will be 0, 0. The second time step will be 0.01559 as well as 0. Then we have 0.0156 with a pressure of 79.5 psi, and then we will have 0.02180 and 0. So this looks identical to what we just saw in the PowerPoint. Now, the program doesn't allow you to put two values here for this particular 15.6 milliseconds. So I had to offset this by a very small value, but more or less, this is that instantaneous rise in pressure for our front wall, and we are complete here. The next time diagram, we will simply take a copy of the front wall and we will rename this to side wall and roof. So going back to the PowerPoint, let's get a quick refresher on what this should look like. Remember, the time diagram really looks identical to what we just saw for the front wall, with the difference that our pressure is going to be much less here, only 24.9 compared to the 79.5 for the front wall, because this blast wave is just sweeping over these surfaces rather than reflecting. So once we have these input points here, we go back to RFEM. And remember, the time is going to stay the same in this first column. All that we need to do is to go ahead and change the magnitude here, or multiplier, to 24.9. And here is our second time diagram. Now, the third time diagram will be for our rear wall. And what I want to do, once again, is to refer back here to a nice summary. We don't necessarily have that instantaneous rise in pressure, but rather we're going to see a linear rise in pressure over a certain time period, and then a linear decay back to zero for this rear wall. And this is also occurring quite a bit later in time, relatively speaking, than what we're seeing with the front wall, as well as the side walls and roof. So we want to take note of all of these various points. We can see here that our max pressure is only 4.6 psi, so much, much lower. So going into this last time diagram, we want to input in our points here. So we'll choose 0, 0. The second point will be 0.0660. The third point will be 0.0779 and 4.6 psi, and then 0.097 and 0. And it looks like we lost that one, 0.097 and 0. Okay, so here is our time diagram for our rear wall. Now, notice that these are just multipliers. So when I say 4.6 psi, all that we're going to end up doing is relating it back to those load cases that we set in RFEM with 1 psi. So that's what I said. It was important to use 1 psi because we'll use this multiplier to affect the magnitude over the time duration. All right, so once we have input all three of these time diagrams, we can finally move on to the dynamic load case tab. And this first dynamic load case, I will title linear. And notice only our linear solvers are available to us. Now, the rest of these that are grayed out are all related to the other dynamic add-on modules that we do not have activated. We will be utilizing a linear implicit Newmark analysis solver, and notice that the natural vibration case is completely grayed out here. That's because we do not use this information for this particular solver. This is in comparison to the linear modal analysis, which heavily depends on that natural vibration case. So with the Newmark analysis, we can move on to the time history analysis. Now, this is where we are going to relate those load cases back in RFEM. So remember the front wall area loads, and then we had the side and roof area loads, and finally the rear area load. We relate this to the relevant time diagram. So the load case here, front wall, is going to be related to my time diagram front wall. This is telling the program how to adjust the magnitude over the full duration of this blast analysis. The second set will be our sidewall roof related to our sidewall roof. And finally, we have here our rear wall, which will be related to our rear wall. Now, as far as the saved time steps, when we set this to a higher value, it really has nothing to do with the analysis. It's just what is going to be shown to us back in RFEM when we review the results. And by setting this to a larger number, we're definitely going to reduce the file size. It's going to shorten the calculation. But if we do not have enough time steps, then we're not going to accurately capture the results. So some of those max and mins, we want to have nice smooth curves for something like our time course monitor. So for example, today we'll set this at 0.001. Now, the maximum time will only be 0.5 seconds. This is a very short duration, and we don't need to set this to something like 10 seconds, 20 seconds, because everything is happening so quickly in milliseconds that 0.5 seconds will accurately capture what's going on with the structure response. Now, the time steps for calculation, this is important for the analysis internally, and it's really a compromise between calculation time and accuracy. So there is the automatic option. You can refer to our help file if you're interested in determining how the program will set this automatic time step, but I think for something like a blast analysis that's such a short duration, it's a little bit better to have full control over what time step you're using. Now, I always suggest to run a time step study. And what I mean by this is to set a time step, run the calculation, view the results, then go back in, set the time step to something even smaller, run the results, and then compare those two. And if you're seeing significant changes between the results, then you know that you need to continue reducing your time step in order to get accurate analysis. But in turn, if we're not seeing much different in the results at all, then surely keep your time step at that higher value for a quicker calculation time. And we'll see a little bit later on that for a nonlinear analysis, this will require a much smaller time step. For today, for our linear though, we can set this as 0.001. We do have the ability to export out load cases here for each one of these time steps. And you can see that when I go into the details, I can turn on and off the various time steps that I'd like to export out as load cases. But keep in mind, it's a little deceiving because we're not exporting out the loads. We are exporting out the results for the selected time steps. So we won't be doing that today, but the other option is to export out a result combination. So this is going to be an envelope solution for all the time steps that we've considered here. We can combine those result combinations with additional static loads if we'd like. The calculation parameters. Remember, the program knows nothing about the natural vibration case based on the Newmark implicit solver. So we need to redefine the acting masses here. We leave this as we've already set before, mass case 1, diagonal matrix for translational degrees of freedom. And finally, we have our damping consideration. So when we're talking about the Newmark solver, we have to think about damping in terms of Rayleigh. And most of us are likely more familiar with Lear's damping. So for a steel structure, Lear's damping might be around 2%. We just need to do a simple conversion here, and it's actually an equation with two equations, two unknowns. We can easily calculate both this alpha and beta based on the Lear's damping that we want. And alpha is going to relate to the mass portion of the damping matrix, while beta is going to relate to the stiffness portion of the damping matrix. So we can either do that manual calculation ourselves, or we have a nice tool in here. And this tool allows me to input in a couple different mode shapes here for the angular frequency, as well as my desired Lear's damping. So this is why I have saved in the background here mode shape 13 and mode shape 18. Remember, those were my dominant modes for that natural vibration case. So I can input in my angular frequency for mode shape 13, which will be 41.48, and the damping considerations will be 0.02 for Lear's, so 2%. Same process for mode shape 18. This time our angular frequency was calculated at 50.35, just given to us here in the background. I want Lear's damping to be 2%. I click OK, and the program automatically calculates alpha and beta for me. Beta may look like its value is 0 here, but we can go into the full precision and see that it's just a very small number, 4.36 times 10 to the negative 4. So once we have input in all of our information for this initial linear time history analysis, we can run our calculation. And for a linear calculation, you can see it actually solves pretty quick. We have our progress bar shown here at the bottom, and we set our time step at every 0.001 seconds. And our total duration is only 0.5 seconds. So once this is done solving, you'll notice that we'll be given back into RFEM here, and I'll go ahead and cancel out this visibility. And we're technically still within this add-on module, RF-DYNAM Pro. We go to table 5 here. Under my drop-down, I have my natural vibration case, but now we have our dynamic load case as well. Right next to that is going to be all of our saved time steps. So if we're looking currently at the global deformation here, and we have time step 0. Well, we can actually scroll through these, and remember, nothing's happening on our structure here until we have that estimated time of arrival at about 0.016 seconds. And that's where we start to see this blast load impact our structure. And we continue scrolling through these different time steps to slowly see that wave load travel from the front of the structure to the center and the roof and clear back to the rear of the structure. Now, for any one of these time steps, or you'll also notice that we have a dynamic envelope up here at the top, all of our results are going to be given to us in table format. So we'll see here member internal forces, we can view node deformations, stresses on our surfaces. We can export all of this information to Microsoft Excel at the click of a button if we wanted to do some further sorting. We can view all of this information graphically here as well with our project navigator. What I think is most of interest is a time course monitor, though, when we're talking about a time history analysis. So with a time course monitor, we can go ahead and launch that directly from our table tools here. And I can graphically select on a single node, for example. And with this node, you'll notice the program automatically updates my time course monitor. Let us take a look at the acceleration in the Y direction. So we can see here the acceleration at this particular node shown over the full duration of the 0.5 seconds for our time history analysis. And if we want, we can turn this to, let's say, displacements in the Y direction. So we're seeing these large displacements and they're slowly dissipating over time. We also have the ability to hold down our control key, and we can select multiple nodes if we'd like to generate them on this same time diagram. So you'll notice that those will just be overlaid here. We can right click, view these as numeric values, and we can export this information to Microsoft Excel as well. So it's pretty powerful what we can do within these various time course diagrams. Now, also within this option here is the ability to view animations. So if we take a look at our structure and we'll turn on our animation mode, we can see that when we play this and we kind of turn on our global deformations here, that we're going to see the structure response of these deformations over time. So we'll just be able to see how these surfaces and members are moving. You can see that the time course monitor is slowly moving from time step to time step. So again, this information that is plotted here is important for those saved time steps to make sure that we get nice smooth curves here for our particular analysis. The other thing that is of interest to us is some of the internal forces for our members. So for this, let me turn off the display of our surfaces just so we can get a clear view of our member elements here. And we'll select this member, one of our front beams. We can take a look at our moment, for example, about the global x-axis. And we can see we're definitely seeing higher moments at early on with this blast impact analysis, and then it will slowly dissipate over time as well. If you remember, what else is of interest to us is this tension-only member. And with the tension-only member, we technically should see only tension forces. So I'm taking a look at this within this time course monitor for my normal forces for member number 74, and we can see it highlighted here. But here's the problem. We're seeing compression forces of -2.64 kips. that is telling me that this cable element is taking on a compression load of 2,600 pounds. And we certainly know that that cannot be the case. So why is this? Well, this is just simply a limitation of the linear solvers. Any nonlinear element, so when we're talking tension-only members, they are going to be automatically converted into truss elements for the linear analysis. So the program only knows what it knows, and if it sees a truss element internally, it's going to think, okay, well, then it can take on these high compression loads as well. There's nothing stopping it. Same thing with nonlinear supports. So if we have supports that are failing in uplift, sure, that's easy enough to define in RFEM for the static analysis, but this linear solver will convert it to a linear support when it runs the dynamic analysis. And finally, something like nonlinear materials. So plastic materials for steel design will be converted back to linear elastic materials. So how can we overcome this if we know that these nonlinearities are extremely important for our blast design? And this is where we're going to go back into the add-on module. So we can go up here to the current module, RF-DYNAM Pro, and we're going to activate here Nonlinear Time History for time diagrams. And you'll notice that none of my tabs changed here. In fact, my time diagrams that I previously defined, we're going to use those again. Under the dynamic load cases, I'm only going to make a copy here of my linear load case, and we'll call this one nonlinear. What the nonlinear time history add-on module extension does is it releases these two nonlinear solvers. So now we have the nonlinear implicit Newmark analysis as well as the explicit analysis solver. Now for something like a blast load, an impulse load, it is suggested to use this explicit analysis, and that's what we'll be using today. Under the time history analysis, again, because we made a copy, nothing changes here. The only modification that we want to make is the time steps for calculation. And remember, I said that when you consider a nonlinear analysis, this requires a much, much smaller time step. That's just because we have these extremely rapid changes under such short durations that you have to have a very small time step to accurately account for this. So under the full precision here, we make this so small, in fact, that it will be 1 times 10 to the minus 6 power. So very, very small. Realistically, under calculation parameters, notice only the diagonal matrix is available for this particular explicit solver. And for damping considerations, we can leave this the same, but the program will only use the alpha coefficient for, again, this particular solver. So as you can imagine, this is going to take a little bit longer to solve than what we saw with our linear. So what I went ahead and did is to run the results for us and open up a saved model here. So once those results are done running, we'll be given back into RFEM once again. And in my table 5, I now have my natural vibration case, my linear dynamic load case, but now I have my nonlinear dynamic load case available to me as well. Now, we don't need to cover all of the various ways to view the results. It's identical to what we just saw with our linear analysis. But what might be interesting to us is if we go ahead under the Views tab and we turn off our surfaces here, and let's focus in on that tension-only member. So I'm going to launch my time course monitor. I'm going to select that particular member that we saw before. It doesn't matter whether we choose 0 or 29.15, the start or end of the member, but I do want to view the normal forces. And now you can see how drastically different this looks. This member is only taking on tension forces. The minute that it sees any type of compression, it's taken out of the analysis, but when tension is reintroduced into the member, it is activated again. So we're only seeing those positive forces here. We also have the ability, if we take a look at our results tab here, and let's activate the animation. I thought this might be interesting for you guys to see, that when I go ahead and run the global deformations here for the structure, you can actually see the element, and let me also turn this into wireframe view. These two elements are deactivated and activated, so you can see them graphically turn on and off as we move through the total duration of this time history analysis. So certainly a big advantage here if we have those nonlinearities that we want to account for with this blast analysis or any type of nonlinear time history, we would want to utilize these nonlinear solvers. All right, so that will bring us to the end of our presentation today. As always, I know that was quite a bit of information. If you're interested to learn more about RFEM or these dynamic add-on modules, you can visit our website at delubal.com. I also have uploaded this webinar model that you saw today, as well as the presentation slides you can find on our website where you registered for this webinar as well, and the recording will usually be posted within a day or so. You can also download the RFEM 90-day trial version. So it's free, it's a full 90 days, and it's full capability that includes RFEM in all add-on modules. So you could download this model today and open that up in the trial version if you're interested in following along at a later time. Our phone number and email for our Philadelphia office are shown at the bottom of the screen. So if you have any questions about today's presentation or anything to do with the Delubal products, feel free to reach out to us here. The phone number is 267-702-2815, and our email is info-us@delubal.com. And again, this is all over our website as well. So we will have many more upcoming webinars. You can register at delubal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week or so before these will take place. So feel free to register directly through the email as well, and keep an eye out for that within the next month or two. As far as PDH certificates, these will automatically be emailed to all participants who are here for the full presentation. So this is a requirement of the states that we are pre-approved providers for, that all attendees are here for the full duration of the webinar in order to receive that PDH. So no need to worry about that. Those will be sent to you typically within the next day. It won't be automatic, so just give it a little bit of time with that. Now, if you did watch this webinar with a colleague and you yourself did not register for the presentation with your own name and your own email address, and you were here for the full 60 minutes, feel free to request that PDH at info-us@delubal.com. Again, info-us@delubal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next presentation. Thank you.